Tonight's subject or topic, as Tim said, is principles of reliability-centered maintenance. This session will be a little bit more philosophical, if you will, than nuts and bolts, than what I usually do. But I want to talk about the basic philosophy of maintenance called reliability-centered maintenance that is sort of is the underpinning of almost everything I do in this field. Reliability-centered maintenance is, I guess you could call it the science of doing exactly the right amount of maintenance, or the science of getting the best possible maintenance for the minimum possible expense, or the science of achieving more safety and better dispatch reliability by doing less maintenance. But it's a maintenance philosophy that is not new by any means. Its origins were almost 50 years ago, in the late 60s and early 70s, in work that was done at United Airlines by two scientists who worked for United, named Stan Nolan and Howard Heap. Stan was an aeronautical engineer, and Howard was a mathematician. And this was about the time in the late 60s and early 70s that United was in the throes of, United and all the other airlines were in the throes of switching over from the big recips to the first transport category jets. For most of the air carriers, that was the Boeing 707, but for some of them, including United, it was the DC-8. And during that period of time when they were changing over to jet equipment and making massive changes in their maintenance operation, they tasked these two scientists, Nolan and Heap, with doing a study of how maintenance was being done at United Airlines, and coming up with recommendations as to how United could do their maintenance in a more cost-effective manner. The interesting part of this was that neither Nolan nor Heap had any maintenance background whatsoever. As I said, Stan Nolan was an aeronautical engineer, and aeronautical engineers, I believe, are not permitted by statute to talk to maintenance people. And Howard was a mathematician, and the reason that they got him on this project was because United had been collecting vast amounts of data about their flight operations, their maintenance problems, and that sort of thing. But nobody had ever really done much analysis of all this data. So they tasked Stan and Howard with trying to figure out whether there were things that United could do better. And the more they looked at the way United was doing maintenance, the more they scratched their heads and wondered why things were being done that way. And I'll get into what they found and what recommendations they made, but the recommendations that they made revolutionized the way United did maintenance. And during the 1970s, basically all the airlines changed over to using the methods that United had developed, and the work that Stan and Howard started at United moved to the Air Transport Association, which is the alphabet group that represents the air carriers, and is codified in a report that is known as MSG, which is in its third major revision. But that report, which is basically the result of the work started at United, is the Bible that is used to this day for developing maintenance programs for transport category aircrafts. MSG stood for the Maintenance Steering Group, which was the group in Air Transport Association that took over the work of Nolan and Heap at United. In the 1980s, this maintenance philosophy of reliability-centered maintenance was adopted by the military. In fact, the Pentagon went to United and asked them to have Nolan and Heap write a report for the Pentagon telling everything that they learned. It's a big, massive thing, many hundreds of pages long. It was issued in 1978, and by the end of the 80s, pretty much all military aviation maintenance was being done in this new fashion. And in the 90s, the same philosophy became adopted by many non-aviation industries that were in fields that were maintenance intensive and safety critical, much like aviation is, because the principles that Nolan and Heap came up with basically apply not only to aviation but to anything that is maintenance intensive and safety critical. So today, the maintenance programs for things like nuclear power plants, chemical plants, oil and gas refineries, water treatment plants, all sorts of maintenance intensive and safety critical industrial applications are done using the principles of reliability-centered maintenance that were invented originally at United Airlines in the late 60s and early 70s. This is sort of a gross timeline of the evolution of maintenance philosophy, if you will. Where first generation maintenance back in the dawn of aviation was basically fix it when it breaks. Then around the World War II era, a second generation maintenance philosophy evolved that was based on trying to prevent failures from happening as opposed to simply fixing things when they broke. Those basically involved various kinds of scheduled preventive maintenance and scheduled life limits or overhauls where various components, engines and so on, would be retired from service at a particular number of hours in an attempt to head off any possible failure. And then, as I said, starting in the late 60s at United and then propagating throughout the airlines in the 70s, this third generation of maintenance, which we call reliability-centered maintenance, was developed, where the focus was not on time-directed things and scheduled preventive maintenance, but was on doing condition monitoring, trying to predict when failures would happen, trying to catch them at the incipient phase and head them off, and a bunch of sophisticated stuff called failure mode analysis, failure effects analysis, that we'll be talking about as we proceed this evening. Now, where we are today is that all the airlines, all the military, high-end general aviation, Gulfstreams and Citation X's and so on, are all doing maintenance today using reliability-centered maintenance. But unfortunately, the low end of the aviation food chain, where most of us hang out, piston general aviation maintenance, is still being done pretty much the same way it was in the 50s and 60s. And we have not adopted this new way of doing things. And one of my missions in life is, and the reason I do these webinars, and the reason I run a maintenance management company, and the reason I do all my talks at AirVenture is to try to drag our maintenance in piston GA, kicking and screaming into the 21st century, so that we can take advantage of all the stuff that has been learned by the more sophisticated parts of aviation over the last 50 years or so. Just to give you an idea of the impact on the air carriers of adopting reliability-centered maintenance, there are a couple of interesting statistics here. The DC-8, which was the last air transport airplane that was developed back in the pre-RCM days, when maintenance was done in the traditional way, the way pretty much that is still in effect for piston GA. For the DC-8, there were 339 components on the airplane that were subject to scheduled overhaul or scheduled replacement. That is, they had a life limit or a TBO or something that caused those components to be taken out of service voluntarily when they reached a certain age, a certain number of hours or cycles or months. On the DC-10, which is a later airplane that was developed in the era of RCM, there were precisely 7 components that had TBOs or life limits. And by the way, none of them were engines. The airline stopped overhauling engines at a particular TBO a long time ago, and everything is done on condition. Here's another interesting one. The DC-8, again, the last airliner that was developed back before RCM became the way of doing maintenance. The maintenance program from Douglas on the DC-8 required a mind-boggling 4 million man-hours of structural inspections during the first 20,000 hours time in service of the airplane. 4 million man-hours of inspections is a number so large that it's very difficult for me to get my brain around it. The Boeing 747, obviously a much larger and more complicated aircraft that was developed in the RCM era, during the first 20,000 hours required 66,000 hours of man-hours of structural inspections, a number that is almost 2 orders of magnitude smaller. So as you can see, that the advent of RCM drastically reduced the amount of preventive maintenance and drastically reduced the use of things like life limits and TBOs. And as a result, RCM has saved the airlines a fortune by, again, slashing the amount of scheduled preventive maintenance to a tiny fraction of what it used to be, and eliminating most component life limits and TBOs in favor of an on-condition approach, where the emphasis is on inspection rather than life-limiting things. Now, it was not a surprise that this change in philosophy saved the airlines a lot of money. That's exactly what it was supposed to do, and what Nolan and Heap were originally tasked to do for United, was to figure out a way that they could do their maintenance more cost effectively. The thing that was not expected, and that came as a rather big surprise, was that when they went to this new method of doing things, where they eliminated TBOs and they drastically cut down the amount of preventive maintenance they were doing, they found that the safety and dispatch reliability of the aircraft improved dramatically. In other words, the less maintenance they did, the more reliable the aircraft were. That was not an expected result, and it certainly wasn't a result that the maintenance people were very happy with. But it was very clear, and at first people scratched their heads to try to figure out how can doing less maintenance rely on a more safer and more reliable aircraft. But when you think about it, the answer was obvious. The less maintenance you do, the less likely it is that you're going to have maintenance-induced failures. And for those of you who attended my webinar in December that was specifically on the subject of maintenance-induced failures, you know, because we spent a lot of time talking about it, that maintenance has this dark side. It's inherently invasive. When mechanics swing wrenches on airplanes, they often break things that were previously working just fine. And when that happens, in other words, when we have a mechanical failure of an airplane that is caused by a mechanic, we call it a maintenance-induced failure. The incidence of maintenance-induced failures is much higher than most people like to think about, and the more invasive the maintenance task, the more likely it is that the mechanic is going to break the airplane. And as I said, if you participated in our webinar last month on this subject, we spent the better part of an hour going through all sorts of incidents where airplanes came falling out of the sky because something that a mechanic did. And if you didn't participate in it, it was an interesting session, and you might want to go back and review the video. But in any case, RCM is a major paradigm shift, a major shift in the way we think about maintenance. The traditional view, pre-RCM, and what most general aviation mechanics believe to this day, is that maintenance is a good thing, and the more of it we do, the better. Maintenance is a good thing, like let's say like exercise, and the more of it we do, the better. The view of RCM is totally different. Is that maintenance is a necessary evil, like surgery, that has a lot of risks involved with it, a lot of costs involved with it, and the less of it we do, the better. Now, obviously, we have to do maintenance, but we should only do it when it's absolutely necessary, or when we've done a careful cost-benefits analysis, and the benefits of doing a particular maintenance task clearly outweigh the costs and risks. And if any of you are physicians, you know that this sounds very familiar, because this is what in medicine is called evidence-based medicine, where we carefully analyze the benefits of a medical procedure against its costs and risks before we decide whether to do it or not. And what RCM is to maintenance what evidence-based medicine is to medicine. One of the basic underpinnings of reliability-centered maintenance is what's called failure mode and effects analysis. What that means is that for every component of an aircraft, we need to analyze the different ways that component can fail, what we call the failure modes of that component. And then for each failure mode, we need to determine how likely those failures are, because the more probable the failure, the more aggressive we want to be in trying to prevent it. Also, and perhaps even more importantly, how serious those failures are. What are the consequences of the failure? If the failure happens, is it going to make the airplane fall out of the sky and maybe hurt or kill someone? Is it just going to put the airplane on the ground? Or is it a failure that is tolerable, and we don't need to really do anything about it until a good, nice, convenient time to fix it? And finally, we need to analyze for all the different failure modes of all the different components whether those failures can be predicted and prevented. In other words, whether there's some kind of condition monitoring technique, some sort of inspection that we can do, some sort of instrumentation we can install that will warn us when the component is approaching failure, and let us take preventive action at that point, at the point where the failure is incipient and hasn't yet affected the operation of the aircraft. One of the most important parts of failure mode analysis is to determine the relationship between failure probability and component age. For various failure modes, we need to know whether that failure is most likely when the component is old, which we call age-related failures, or whether it's most likely when the component is young, which we call infant mortality failures, or whether the probability of failure of the component is unrelated to the component age and happens with equal probability, regardless of whether the component is new or old or something in between, which we call a random failure. And it's, as you'll see, it's very important for us to determine what the relationship is between failure probability and component age, because it will radically affect how we try to prevent the failure, or even if we try to prevent the failure. Another very important aspect of reliability-centered maintenance is what's called failure effects analysis or consequence analysis, where we look at the different kinds of failures that can occur and try to determine how serious they are, what their consequences are. And we can classify failures into 3 or 4 basic categories. The most serious failures are what are called failures with safety consequences, where the failure might hurt or kill someone. For example, a catastrophic engine failure, a wing spar failure, or failure of any primary airframe structure. Those would be considered failures with safety consequences, and they're the most serious kinds. Then one step removed from that, one step lower on the hierarchy, is what are called failures with operational consequences. They're failures that aren't going to hurt or kill someone, but they might leave us stuck somewhere. They might leave the airplane stuck in an unflyable condition. For example, if a magneto fails in flight, we have 2 of them. So it's the likelihood that a magneto failure is going to hurt or kill someone is fairly low. But once we land with a bad magneto, we're not going to take off again until the magneto is repaired. So a magneto failure is a failure with operational consequences. It probably isn't going to get us hurt, but it might leave us stranded in the Motel 6 in Sheep Dip, Nebraska over a weekend when we didn't really want to be there. The lowest level of failure consequences, what are called failures with economic consequences. Those are failures that aren't going to hurt or kill anybody. They aren't going to get us stuck anywhere. They're just going to cost us money to fix. For example, failure of a number 2 comm radio. It's not going to cause us to ground the airplane or cancel our trip. It's certainly going to cause us to fall out of the sky. But when we get the airplane back home or to an avionics shop, we're just going to have to get it fixed. As a general rule, we need to know what the consequences of failures are, because we want our preventive maintenance strategy to be proportional to the consequences. In other words, we want to focus our maintenance dollars on preventing the serious problems, and not spend a lot of money on trying to prevent problems that have acceptable consequences or acceptable failures. So failures with safety consequences that might get somebody hurt or killed, we can't allow to happen, and we must do whatever it takes to prevent them, even if it's very expensive. Failures with operational consequences aren't nearly as serious, but because we don't particularly want to get stuck in Sheep Dip, Nebraska over a weekend in a Motel 6, it's probably worth spending some effort and some money to try to prevent that kind of failure. But the vast majority of failures are failures with only economic consequences. There's no reason for us to be trying to prevent such failures. Nobody does inspections of their number 2 comm radio every 6 months to try to head off failures. We just run those devices until they fail, and then we fix them when they do. And in the RCM way of doing things, a strategy called run to failure is a legitimate strategy, and is the optimum strategy for any failure mode that does not have serious consequences. So a big part of RCM is trying to sort through all of the things that can go wrong and decide which ones of those are worth spending money to prevent. And an awful lot of them turn out to be not worth spending money to prevent. Now, if we have a failure mode that is worth trying to prevent because it has unacceptable consequences, there are 2 basic alternative strategies that are used for preventive maintenance. One is called time-directed maintenance. Time-directed maintenance attempts to avoid failures by retiring, or replacing, or overhauling components when they get to a certain age, a TBO or life limit or something like that. An alternative strategy is called condition-directed maintenance. And condition-directed maintenance attempts to avoid failures by monitoring component condition using some sort of inspection or test or instrument in order to detect potential failures before they become full-blown functional failures. And so these are 2 fundamentally alternative ways of doing preventive maintenance. Now, condition-directed maintenance works only if there is a feasible method for detecting incipient failures. And it turns out that, that there is for most components. Most components can be inspected or analyzed in some reasonable fashion to determine what their condition is and to dealt with when the condition deteriorates to a certain point. But not everything is that way. For magnetos are an example. From a mechanic standpoint, a magneto is a black box, and he has no way of looking at a magneto and determining what condition it's in. The only way we can determine a magneto's condition is to pull it off the engine and tear it down. And so for magnetos, we have to use a time-directed maintenance. Every 500 hours, we tear the magnetos apart and do a detailed disassembly inspection and so on. Time-directed maintenance, on the other hand, works only for age-related failures. In other words, if the most likely time for a magneto to fail is within the first 50 hours after it goes into operation, then tearing it down after 500 hours isn't going to solve that problem. So time-directed maintenance only works for age-related failures, and it's basically useless for infant mortality failures or random failures. And it turns out one of the things that RCM research showed is that the vast majority of failures are not age-related, and we'll look at that in a moment. If both condition-directed and time-directed maintenance are applicable to a particular failure mode, condition-directed maintenance is always much more cost-efficient than time-directed maintenance. So if we have the choice, we always want to go with a condition-directed approach, because a condition-directed maintenance says that we do maintenance when there's a demonstrable problem. In other words, when the condition of something has deteriorated to a point that we've determined is dangerous. Time-directed maintenance is when we do maintenance at a time when somebody guesses that the component may have deteriorated. And the people who do the guessing, which are usually the aircraft manufacturers who set the TBOs and set the timetables for doing various kinds of time-directed things, generally set those times very, very pessimistically, because the times that they set have to work for all the airplanes in the fleet, including the worst-case airplanes. So they generally are way more conservative than they need to be for most of the aircraft in the fleet. So in any case, if we have the choice between doing something on a condition-directed basis or doing it on a time-directed basis, we always want to choose condition-directed because it's much more cost-efficient. It only causes us to do maintenance when there's a demonstrable reason for doing it rather than on some fixed timetable. So when we design a maintenance program using RCM, we go through a decision tree that looks something like this. For a particular failure mode of a particular component, the first thing we ask is, how serious is that failure? Does it impact safety? Does it impact the mission? Could it cause us to get stuck somewhere? Does it risk collateral damage if the failure happens? Could it cause other consequential problems? And if the answer to all those questions is no, then the optimum strategy is not to try to prevent the failure. Just let it happen and fix it when it does. In other words, run to failure. On the other hand, if the answer to any of those consequences questions is yes, if that failure is a safety problem or an operational problem, or it risks serious consequential damages, then the failure is an unacceptable failure, and we have to try to do something to prevent it. So the first thing we ask is there some condition-directed approach that we can use to catch failures at the at the incipient stage before they cause problems? Is there some sort of inspection? Is there some sort of measurement? Is there some sort of test? Is there some sort of instrumentation we can install that will alert us to deteriorating condition before it gets bad enough to cause a failure? And if the answer is yes, and it is quite a bit, quite often yes, then we implement whatever that condition monitoring approach is. And when the condition monitoring tells us that something has deteriorated beyond acceptable standards, whether it's a compression check that's 40 over 80, or if it's or the free play in a trim tab is greater than the maximum acceptable amount, or whatever, then we perform preventive maintenance to correct that situation before there's some sort of serious failure. On the other hand, if there is no practical way of doing condition-directed maintenance, say a magneto, then we ask, is there some time-directed approach that would be effective in eliminating or reducing the failures? Can we set a life limit? Can we set a TBO? Can we do a periodic teardown inspection at a particular number of hours or a particular number of months that would help reduce or eliminate those failures? Now, the answer to that question will be yes, only if the failures are age-related. But if the answer is yes, then that's what we want to do. So, for example, in the case of magnetos, we tear them down every 500 hours because we have no non-invasive condition monitoring approach that we can use to determine magneto condition. Magneto failures are typically age-related, and so we have no choice but to put a fixed number of hours and say after 500 hours we're going to tear down the mags. Now, if it turns out that there is no time-directed method that is effective, no condition-directed method and no time-directed method, so for example, if the failure is not an age-related one, then we got a problem because we've got an unacceptable failure, and neither condition-directed preventive maintenance or time-directed preventive maintenance is going to let us prevent those failures. So at this point, we have to either accept the failure, which we don't want to do because we've already said it's not an acceptable failure, it impacts safety, or it impacts the mission, or it risks collateral damage, or we need to redesign the system, typically by adding redundancy, so that the failure becomes an acceptable one. So for example, if a failure of a vacuum pump that's driving our attitude gyro is a very intractable failure for which neither condition monitoring nor time limits is effective in eliminating the failure. And we talked about that in an earlier webinar. So what do? We have to have a backup pump, we have to add redundancy, or we have to have a backup attitude indicator that's electrically powered rather than vacuum powered, or do something so that the failure, for that particular failure mode, the failure of the vacuum pump, becomes an acceptable failure. And then at that point, we can go ahead and simply run the pump to failure because we have enough redundancy that failure of the pump is not going to be a big problem. We talked about the importance of determining whether failures are age-related. And one of the big changes between the traditional view of maintenance and the RCM view is that in the traditional view it was assumed that most failures were age-related, and that components started out fairly reliable, where the probability of failure was low, and they remained reliable for some useful life, after which, if you kept the component in service long enough, its reliability would start deteriorating, and the probability of failure would start increasing. And if you kept the component in service long enough, the probability of failure would become unacceptable. So we tried to, in the traditional view, we tried to establish a useful life for each component, and then establish a TBO to voluntarily take that component out of service before it got into this wear out zone where the probability of failure started to increase. And this was the basic model for which the traditional maintenance, what we call second generation maintenance philosophy, was based. And so everything was based on time-directed stuff and life limits and TBOs and so on. But one of the discoveries of RCM research was that this is really not the way most failures happen. For example, consider our piston aircraft engines. Do they exhibit this sort of a failure pattern? And the answer is no, they don't. How do we know? Well, we know from research. We know from, for example, from NTSB accident data, and I've shown this in other webinars, so I won't spend a lot of time on it. But this was a study that was done by a failure analysis expert, Nathan Ulrich, a PhD up in Maine, who analyzed 5 years worth of NTSB accident data for small piston aircraft to try to determine what the relationship was between engine failure accidents and how much time was on the engine. And when he analyzed it by hours since the engine was new or rebuilt or overhauled, the pattern was very clear that by far the most likely time for an engine to suffer catastrophic failure is when it's young, in the first few hundred hours after it's built, rebuilt, or overhauled, or otherwise invasively taken apart. And that as you get more time on the engine, the probability of failure monotonically decreases. When you look at the same thing by calendar years since the engine was built, rebuilt, or overhauled, the pattern is even more dramatic. And by far the most likely time for an engine to fail catastrophically is in the first few years after it was built, rebuilt, or overhauled. And the older it gets, the less likely it is that it's going to blow up and make you fall out of the sky. And we need to be careful about how we interpret this information, what conclusions we draw from it, because it should be no surprise that there aren't a large number of catastrophic engine failures on very, very high time engines past TBO, simply because the current maintenance culture is that we voluntarily retire these engines. I mean, the engines on my airplane are more than double TBO, but there aren't a lot of people flying with very, very high time engines like I am. And so it's only natural that there aren't a lot of engine failures way out on the right side of these curves, simply because most people euthanize the engines before they get that far. But what is striking is the very, very high incidence of infant mortality in the left side of the curve when nobody has voluntarily taken their engine out of service. And if you have a failure in the first 500 hours or the first 4 years after an engine is built or rebuilt or overhauled, it was a catastrophic failure. It wasn't a voluntary matter of voluntary euthanasia. So it is very clear that with our piston aircraft engines, without question, the most likely time for us to have a failure with serious consequences, an engine failure with serious consequences, is when the engine is young, not when the engine is old. And there's just no question about that. So a more accurate, not totally accurate, but a more accurate picture of what our risk curve looks like, say on a piston aircraft engine or on a lot of the components, is a curve like this that engineers call a bathtub curve for obvious reasons, where there are two areas of high risk of failure. An area on the left side of the curve called the infant mortality zone, when the component is relatively new and untested, if you will. and an area way out on the right side of the curve when the component is old. It's called the wear-out zone. And when you have a curve like this, the question is, well, does it make sense to overhaul a component like this at TBO? And the answer is it's a very difficult question, because the purpose of overhauling a TBO is to try to avoid the risk of going into the wear-out zone. But by doing it, you're voluntarily putting yourself right into the infant mortality zone, where we know the risk is very high. So whether or not it makes sense to overhaul a component like this at TBO really depends on the relative risks of the infant mortality zone and the wear-out zone, and how steeply the curve is sloped out at the right side, and so on. And unfortunately, we don't have very much data about that. We've got tons of data on low-time engines, and we know that the failure rate on low-time engines is extremely high. We have very little data on very high-time engines, because most people voluntarily take their engines out of service at TBO, and there aren't a lot of people like me that are running them way far out on the right side of the curve. So we're a lot less sure what that curve looks like. But what the slope of the curve is makes a huge difference. If it turned out that the slope of the wear-out zone curve was very shallow, and for example, for turbine engines, we know it's very shallow, then it wouldn't make any sense to overhaul an engine at TBO, because the risk of continuing it in service is much less than the risk of overhauling it and putting it back into the infant mortality zone. And that's why we don't overhaul turbine engines at TBO anymore, and why I don't believe that we should be overhauling piston engines at TBO. One of the really interesting things that was done by a number of RCM researchers, originally the Nolan and Heath study at United Airlines, and subsequently several other studies that were done by other researchers, was to try to look at a very large cross-section of aircraft components and try to figure out what the shape of the curve looked like. And here are some results of two studies, the one that was done at United Airlines, and another one that was done 5 years later by a guy named Bromberg. And they came up with slightly different numbers, but they were all strikingly similar. And there have been subsequent studies by the military that all kind of reinforce this. And they identified basically 6 different curve shapes, 6 different families of curve shapes that represent the different sorts of risk curves that you can have for various components. 3 of them, the ones on the left, are non-age-related failures. That is, the curves don't go up at the right-hand side. And the ones on the right are all curves that have an age-related failure component, that when you get way out to the right side of the curve, the risk of failure goes up. And as you can see, depending on which study you used, somewhere around 90% or so of all of the components that were studied turned out not to have any significant age-related failure mode. In other words, trying to life limit them or put a TBO on them or something like that wouldn't help. And in the vast majority of cases, it would hurt, because by far the largest probability of all is that curve on the lower left, where the primary risk is infant mortality. Something like 2/3 of all components studied had a significant infant mortality risk and no identifiable age-related risk. The curves on the right side have an age-related component to them. The one on the top right is that bathtub curve we just looked at. The one below it is sort of the classic age-related curve. But note that classic curve only applied to 1 or 2% of the components that were studied. It's very unusual. It does apply to things like wing spars, but it doesn't apply to most aircraft components. And there are really only 4 to 6% at most of components on a civil aircraft for which TBOs or life limits would make any sense. because for most components there just isn't significant age-related risk, and if there is an age-related risk, then life-limiting or TBO isn't going to help. And if there's significant infant mortality risk, it's going to hurt. Another thing that the RCM researchers identified was sort of the kind of an intrinsic notion that some components are simple and others are complex. Simple items are ones that have one dominant failure mode. In other words, if this component fails, it almost always fails the same way. For example, a wing spar. If a wing spar fails, it almost always fails through repetitive stress metal fatigue. And for such simple items that have one dominant failure mode, it turns out that the failure probability often is age-related, predominantly age-related, and that for those sorts of components, like primary structure, an age limit or a safe life limit or a TBO, some sort of a voluntary retirement of the component after it reaches a certain age, may be useful in eliminating failures. And that's why almost all newly designed general aviation airplanes that are designed under Part 23 rules, like the Cirrus and the Diamond and that sort of thing, have an airframe life limit as part of their certification basis. On the other hand, complex items, ones that can fail in lots of different ways, and an aircraft engine is the classic example of a complex item where there are hundreds of different failure modes, and you never know which one is going to get you. There's no dominant failure mode for engines. There are just too many different ways they can fail for us to be able to identify any dominant mode that says, if your engine fails, it's probably going to be because blank. You just can't fill in that blank. For complex items with many different failure modes, analysis indicates that failure probability usually doesn't have a major age-related component to it, and we've seen how clearly that's true with piston aircraft engines, and that life limits and TBOs are generally not effective in reducing failures. Yet in the classic view, we believe that they were, and that's why we still have TBOs and life limits on complex items like engines. But we really shouldn't. The research indicates that that's counterproductive. Finally, this is an interesting notion, and this is not a real graph, it's just sort of a conceptual thing that came out of the RCM research. Because RCM is so heavily dependent on condition monitoring, where our emphasis is on inspection rather than on replacement. So the question often arises, how often do we need to inspect something in order to be sure or confident that we will be able to detect a problem before it gets serious? And the RCM researchers came up with this notion of what they call a PF interval. The concept here is that a component starts out in good condition and then over time gradually wears and deteriorates. And at some point, the deterioration gets bad enough that we can detect it using whatever test we're using, whatever inspection procedure or measurement procedure or instrumentation we're using to determine condition. And we call the point where we can detect the deterioration to be point P, the point of potential failure. And then if we let the component continue in service, either because we weren't looking, or we weren't looking often enough, or we weren't paying attention, eventually the component will fail, and we'll call that point F. And the question is, how much time is there between point P and point F? In other words, how much lead time does the condition monitoring technique give us before the component fails? And if we can estimate that lead time, for example, just to give you a concrete example, I've done a lot of studies on exhaust valve failures in piston aircraft engines, and in how we can predict exhaust valve failures by doing bore scope inspections. And it turns out that the bore scope, at least based on the studies I've done, starts to indicate a visible hot spot on an exhaust valve somewhere on the order of 100 hours before the valve actually gets bad enough to fail, where a piece of the valve comes off and the cylinder shuts down. So we would say that the PF interval for bore scope inspections of exhaust valves is somewhere on the order of 100 hours. It also turns out that we can usually detect a failing exhaust valve using a digital engine monitor, because as the valve approaches failure, the EGT starts to oscillate noticeably. It's a pretty subtle oscillation, but if you have been trained properly, you can detect it on the engine monitor. And the studies that I've done of that indicate that the engine monitor gives us on the order of 25 hours of advanced notice before the exhaust valve fails. So the PF interval for detecting exhaust valve failures using an engine monitor is only 25 hours. The advantage of the engine monitor is it's watching all the time, whereas bore scope inspections we have to schedule. So the question is, if we want to do bore scope inspections and prevent exhaust valves from failing, how often do we need to do the inspection? And the basic rule of thumb that the RCM researchers came up with is that if we want to reliably detect potential failures and prevent them from proceeding to full functional failure, we should be inspecting at approximately 1/2 the PF interval. So that says that if I'm right and the bore scope gives you about 100 hours of lead time before an exhaust valve fails, then we really ought to be inspecting with a bore scope every 50 hours if we wanted to completely eliminate the possibility of exhaust valve failures, which would basically be doing a bore scope inspection every time we do an oil change. Now, very few people do that. Most people are lucky if they get a bore scope inspection at an annual, and a lot of shops don't do them at all. If you do a bore scope inspection just once a year and you're only flying 75 hours a year, that might be enough. If you're flying 300 hours a year and you only do a bore scope inspection once a year, that's not enough to assure that you will catch exhaust valve failure before it happens. So that's the notion of the PF interval. At any rate, this is a very, very rich subject. There are now many textbooks on the subject of reliability-centered maintenance. If you go on Amazon and look up RCM, reliability-centered maintenance, you'll get a whole bunch of hits. These are a couple of textbooks that I have on my bookshelf that are really quite good. The Nolan and Heap report, which was written by those guys at United, that was the report that the Pentagon commissioned, and it was published in 1978. It's 520 pages long. It is not available in print as far as I can tell, but you can get it in as a big PDF file, a 25 megabyte PDF file from the National Technical Information Service in Washington, and it is fascinating reading because it really is at the very beginning of when all of this stuff was invented. But there's a lot of great reading material if you're interested in learning more about RCM, and I found it absolutely fascinating, and it has had a huge impact on the way I think about maintenance, the way I maintain my own airplane, and the way I advise my clients to do maintenance. Just to wrap this up and give you a couple of specific examples of how you would put some of these principles into effect. Let's consider a couple of different components and their failure modes. dry air pumps, vacuum pumps if you will, one of the most intractable components on our general aviation airplanes from a from a failure standpoint. The traditional approach, the manufacturer's recommendation, is to replace the pump every 500 hours. In my view, that's totally dumb. If you do an RCM analysis of a dry air pump, first of all, what are the consequences of a pump failure? Well, if you have a vacuum-driven attitude gyro and you only have one pump and the pump fails and you're in IMC conditions, the consequences are very dire indeed. And so it's definitely an unacceptable failure, and we can't tolerate it. What is the PF interval? It turns out that there's no meaningful PF interval. There is no way of doing condition monitoring of a vacuum pump that will predict failures. There are all sorts of theories. They have these inspection ports and stuff where you can inspect the vane length. But having studied this situation for about 25 years, I can tell you that vacuum pumps fail when they want to fail. They give you no warning. The pump runs absolutely perfectly right up until it doesn't. And then in a matter of milliseconds, in a big puff of broken vanes and graphite powder, the pump suddenly becomes inoperative. Failure is random, unpredictable. They're life limiting, the pumps doesn't work, condition monitoring the pumps doesn't work, and therefore the only thing that does work is having a backup. You either have to have two pumps, like for example I do on my twin, or you have to have a standby pump that is powered by an electric motor that you can turn on when your main pump fails, or you have to have a backup attitude gyro that's electrically powered so that if you lose your vacuum, you still have a way to keep the dirty side down. And once you have a backup, whether it's a second engine-driven pump or an electrically driven standby pump or an electrically driven backup gyro, then the failure of a pump becomes an acceptable failure with acceptable consequences. So at that point, the logical thing to do with these pumps is run them to failure. So the RCM analysis of a dry air pump is, it makes no sense to replace them on any particular timetable. You have to have a backup, and once you have a backup, you should run the pumps to failure. And that's what I do, and that's what I advise my clients to do. The second example, we just talked about this quite a bit, is exhaust valves. The traditional approach has been to do a compression check, and if the cylinder passes the compression check, everything is assumed to be good. And we have traditionally seen a fairly high incidence of exhaust valve failures. Those failures are fairly serious because if an exhaust valve fails, whatever cylinder it's in no longer can produce power. If you have a 6-cylinder engine and it suddenly becomes a 5-cylinder engine, the engine's going to run very rough, and you're going to put the airplane down at the first available airport and change your underwear. If you have a 4-cylinder engine and it becomes a 3-cylinder engine, there's a high likelihood that you're going to wind up putting the airplane down on a road or in a field somewhere. So this is by no means an acceptable failure. The probability of the failure is very high, and exhaust valves often fail prior to TBO. And retiring the engine at TBO is absolutely no assurance against exhaust valve failures. But we do have at least 2 very good condition monitoring approaches to detect these failures before they become serious. As I indicated, the bore scope inspection, and I get into a lot of detail in the cylinder webinar that I did for EAA with lots of good pictures and stuff. But the bore scope can give us about a 100-hour lead time before an exhaust valve fails. It becomes obviously asymmetrical when viewed under a bore scope, and we know that it has a hot spot and that it's only going to get worse. And if we miss it with a bore scope because we aren't doing bore scope inspections often enough or at all, a digital engine monitor in the hands of a trained pilot who knows what to look for, can give about a 25-hour warning before the exhaust valve fails. So we have two good ways of detecting the failures before they get critical with meaningful PF intervals, and therefore the RCM approach to dealing with this is to perform regular borescope inspections and to train pilots to detect failing exhaust valves using the engine monitor. And if we do those two things, there's no excuse for ever having another exhaust valve failure. And finally, if we look at the engine as a whole, of course the traditional approach in piston GA has been to overhaul the engines when they reach TBO. As it should be no surprise to you, the RCM analysis indicates that that is not a very sensible thing to do. And of course the airlines stopped overhauling engines at TBO decades ago. An engine is the prototypical example of a complex item with numerous failure modes, none of which are dominant. The failure modes of engines include all three kinds of failures. There are age-related failures, there are infant mortality failures up the gazoo, and there are random failures. And we never know which kind of failure is going to cause the engine to fail. But if we look at all those different failure modes, which is exactly what RCM does, we find that the age-related failures are ones that tend to telegraph themselves. When an engine develops an age-related failure, for example, will start making metal. And if we're paying attention to the oil filter and we're sending our oil out for analysis and stuff, we'll get lots of warning of those age-related failures before anything serious happens. And we almost always have enough warning to head the problem off. On the other hand, infant mortality and random failures are often catastrophic and occur without warning. Those are the really scary kinds of failures, which is why when we look at the accident statistics, the great majority of catastrophic engine failures aren't age-related. They occur when the engine is young. I mean, the two things that mostly cause catastrophic engine failures are A, infant mortality that happen when the engine is young, and B, maintenance-induced failures that happen after we let a mechanic do something invasive to an engine. And if we could eliminate those two causes, we'd almost never have engine failures of piston aircraft engines, because the age-related ones are the ones that give us lots of warning. And the only time those are going to bite us is if we're just not paying attention. So the RCM solution to how to deal with piston aircraft engines is to put the engine on a state-of-the-art condition monitoring program, which by coincidence happens to be what our February webinar is going to be about, is engine condition monitoring, and then to overhaul the engine strictly on condition and pay no attention to TBO. So why don't we use reliability-centered maintenance in piston GA? Piston GA is the only remaining segment of aviation that still does maintenance the way it was done back in the 50s. And there are really two reasons for it. One is that A&P schools still teach the old-fashioned ways. There's no discussion of RCM in the A&P training syllabus. There's no discussion of any of these concepts in the FAA knowledge exams or practical tests that somebody has to go through to get their A&P. And the general aviation manufacturers encourage the old-fashioned ways in their maintenance manuals and checklists. Again, the maintenance manuals for these airplanes are similar to the way they were for airliners, back in the 50s and 60s. The GA manufacturers have brought things into the new way of doing things for their high-end airplanes, for the Gulfstreams and the Challengers and the Citation X's, but not for the little stuff, not for the stuff that most of us fly. And they really don't have a lot of incentive, because neither A&Ps nor GA manufacturers have a lot of incentive to reduce the maintenance cost of these airplanes. It's us as aircraft owners that have incentive to reduce the maintenance cost and to do things in a more efficient way. So if there's going to be a change, it's going to have to be brought by us, the aircraft owners. And that's why I do these webinars and do all of the stuff I do, because we are the people who are going to need to change this. Tim, that's basically all I have. I'm ready to open things up for questions and answers.
Okay, great, Mike. We do have a number of questions that have come in.
Was the audio okay?
Yeah, your audio was good for the most part. There's a few people that had problems, but after closing some other applications that were accessing the internet on their end, they seemed to resolve those. So audio was very good. First question here from Raphael, and he's kind of wondering if he only flies his airplane 30 hours a year. He's wondering why he needs to repack those wheel bearings annually during the annual inspection. Does he really need to do that?
Yeah, you really do, and you probably do more than the airplane that's flying 150 hours a year. The issue with wheel bearings is almost completely an issue of corrosion, and we don't wear the bearings out. The problems are almost always corrosion related, and the corrosion is something that occurs when the airplane sets, not when it's active, and it's it's the grease in the bearings that protects it from corrosion. And unfortunately, most of our GA wheel assemblies don't have really good, effective weather seals on them, and they depend almost completely on having the bearings packed with grease in order to protect them from corrosion. So, and how vulnerable you are really is not so much a question of how much you fly, but what the environment the airplane lives in when it's not flying. So, if your airplane was hangared in Denver, I would say you probably could get away with going 2 or 3 years between repacking your wheel bearings. And if it was tied down in Florida, you have to be really religious about doing it every year. But it's really not a function of how active the airplane is. It's really a function of what the corrosion risk is.
Great. Okay, and John has the question. It doesn't seem that there is a bright line between failures with operational consequences and failures with safety consequences in all cases. For example, if flights are VFR and a loss of the vacuum system, it's not a big deal. However, at night or in IMC, it could be a showstopper. Other examples abound. What are the tools that pilots and owners might use, such as criteria or risk factors, to determine whether a part is a safety issue or an operational issue or merely an economic issue?
Well, I'm not sure how to answer that other than saying that's a very perceptive observation, and the consequences of various failure modes is definitely a function of how we use the airplane. So for example, if you confine your flying to day VFR, then quite possibly having a single vacuum pump and no backup may be acceptable, because the failure is not that critical. But if you fly at night or you fly in IMC, then the consequences of the failure is greater. There are even some other wrinkles that complicate this thing. I think we talked about in one of my previous webinars. I think on magnetos. I think I mentioned that although we are required by regulation to have dual magnetos, so that theoretically the failure of one magneto is an acceptable failure, because theoretically we will always have at least one good one. What I found out just in the course of my maintenance management business is that one of the most common failure modes of magnetos is not a failure mode that just causes the magneto to quit and stop putting out spark, but it's a failure mode that causes the magneto to fire the wrong plugs at the wrong time, specifically a failure of the plastic distributor gear. And when a failure like that happens, and the engine starts running very, very rough and gets extremely unhappy, my experience is that almost no pilot has either the proper training or the presence of mind to diagnose the problem and shut off the bad mag. If you shut off the bad mag, the problem would become a non-issue, and you just go ahead and fly to your destination on the good mag. But if you don't have the knowledge or the training to realize what's happening and to shut off the mag that's firing inappropriate spark plugs at inappropriate times, that failure, which really should be an easy one to deal with, becomes a total emergency. And we've had something like a half a dozen of those failures in the last year and a half, just in the fleet of aircraft that my company manages, involving high-time pilots, low-time pilots, CFIs. Some of them were up at the flight level, some of them were down at pattern altitude. And in not one case did the pilot have the presence of mind to realize what was happening and to shut off the bad mag, which would have resolved the problem. And that was even true of one failure that we had of a Cirrus SR-22 that had the mag fail up at flight level 190. And he literally had a half an hour to think about it as he was descending from 19,000 feet down to an emergency landing in Cincinnati. But in that half hour, it never dawned on him to try shutting off one of the mags. So you're absolutely right. The line between failures with safety consequences and failures with operational consequences is a fuzzy line and a very complicated one.
Great. Colleen has a question here. She says, I'm totally on board with condition-based maintenance for engines, and my own Lycoming is currently 400 hours past TBO and running strong.
Yay.
I've heard some naysayers speculate that when it does come time to overhaul, the extra time past overhaul will have damaged expensive parts like the crank or the case, requiring their replacement. Is this an old wives' tale?
It is absolutely an old wives' tale. Let me just quote a couple of quick specifics just to indicate just how old wives' a tale it is. Lycoming did a study on the life cycle of a crankshaft, of a Lycoming crankshaft. As a result of a lawsuit, they pulled the study off their website, and I wish I had grabbed a copy while it was still there, but I remember it very, very vividly. And the Lycoming study indicated that the normal life of a Lycoming crankshaft, assuming that it doesn't undergo some extraordinary event like a prop strike that would compromise its integrity, is that the typical Lycoming crankshaft will go 7,000 hours before it wears enough to flunk dimensional tests. And at that point, after about 7,000 hours, the crankshaft is machined to an approved undersized dimension and installed with undersized bearings, and goes another 7,000 hours, and until it eventually flunks dimensional tests again at 14,000 hours, at which point it finally has to be retired from service. 14,000 hours is longer than the vast majority of us will ever fly in our lifetime. So certainly behind Lycomings. I frankly don't know anybody that's flown 14,000 hours behind Lycomings, although I suspect there might be a handful of people in the world. But for all practical purposes, the lifespan of a Lycoming crankshaft is infinite. Not truly infinite, but it's longer than most of us will fly in a lifetime. Case cracks are not age-related failures in general. We find that cases are either properly designed and properly stress relieved when they're built, in which case they typically go essentially forever, or they have some flaw when they're manufactured, in which case they will crack with some time within a TBO or so. So in fact, crankcases are like fine wine, that if they get to a nice, appropriate, mature age, we know that they're good crankcases and they'll probably last for a very, very, very long time. The only truth to that suggestion that running engines far past TBO will cause the overhaul to be more expensive used to have some truth to it back in the old days when cylinders were very expensive, and it was common practice at overhaul time to overhaul the cylinders rather than install new ones. However, today, cylinders are very inexpensive. They're roughly half the cost in real dollars that they were, say, in the 70s or 80s, and that's because cylinders used to be very labor-intensive to build. Now it's all done by automation and so on, and there's very little labor component involved. And with cylinders, new cylinders as cheap as they are today, almost nobody tries to reuse cylinders at overhaul. Almost every time engines go through a major overhaul, they have new cylinders installed. And so if you're going to put new cylinders on at overhaul, you might as well get every last hour out of the old ones you possibly can. So basically, they're really, to the extent that there ever was truth in the notion that running past TBO will cause the subsequent overhaul to be more expensive, it really has no validity in today's world. Tim, did I lose you?
Okay, oh. Are you there?
Yes.
Okay. Terry has one question here real quick. What does TBO stand for?
Time between overhauls.
Gotcha. Okay.
It's a manufacturer's recommended age at which the engine should be overhauled.
Gotcha. Okay, and a question about your personal aircraft there, Mike. Wondering how much time do you have on your engines? How much past TBO are your engines? And then kind of following up on that, is that a result of you having maybe exceptional skill and more knowledge than just the average pilot operating the engines? So are you getting a lot of time out of yours because you're an above average operator and you have a lot more knowledge than the average person?
Well, that's a complicated question. First of all, I'll start with the easy part. I fly a Cessna Turbo 310 that has a pair of Continental TSIO 520BB engines on it. Continental's published TBO for those engines is 1,400 hours. It's a fairly short published TBO. I think it's short because it's a turbocharged and non-intercooled engine, and so it's an engine that's fairly easy for pilots to abuse. So 1,400 hours is the manufacturer's published TBO on the engines. My engines are now close to 2,900 hours since overhaul, and close to 4,800 hours since new. So the engines are somewhat slightly beyond twice the published TBO, and about 3/4 of the cylinders are the original cylinders that went on the engines when they were new, and have 4,700 and some odd hours on them, which is really quite extraordinary. I have replaced 3 cylinders on those 2 engines, 3 out of 12, since the Engines were originally built in 1979. In each case, because of a cylinder head crack between the top spark plug and the injector boss, which is kind of the standard place that Continental cylinder heads crack. It's not a safety of flight kind of issue because the crack is basically stop drilled at both ends and it's not going anywhere. But once you detect a crack like that, you have to retire the cylinder. And so I, over the 33 years since those engines have been built, 3 out of the 12 cylinders have been retired. Why have I gotten such good life out of the engines? Probably lots of different factors. I fly fairly regularly, although these days I'm not flying quite as much as I did, say, 10 years ago. In the first 10 years or so that I owned the airplane, I typically flew around 200 hours a year. These days, it's closer to 125 hours a year. I do hangar my airplane, although my hangar is 8 miles from the Pacific Ocean, so I live in a fairly high corrosion environment. I think one of the big factors is the fact that I'm very, very careful about how I operate the power plant, and I'm obsessive about limiting cylinder head temperatures and so on. And any of you who have gone through my webinar on leaning and my webinar on cylinders will have more information on that. And I fly it, fairly regularly. Although not as regularly as I'd like. I mean, there are certainly times when the airplane sits for several weeks without flying, but it never sits for months without flying. And that's about all I can say. It's just a combination of factors, and I do think that the fact that it's hangared, it flies regularly, and I'm very, very careful about temperature management are probably the 3 biggest factors. And the fact that I didn't drink the Kool-Aid and euthanize those engines at TBO was probably a big part of it.
Great. Okay, so we're coming to the end of our time here. I'm going to pick out a few more questions here to have. One is from Dan, and he says we're kind of stuck with Appendix D to Part 43 for the annual and 100-hour checklist. Could you comment on that checklist versus RCM?
Well, I mean, I'm not sure exactly what you're getting at. I mean, the FAA does not require us to use the manufacturer's inspection checklist. We can use any checklist we want to put together as long as it contains the minimum stuff that's in Part 43, Appendix D. But what you may be getting at is the fact that for our category of aircraft, that is piston engine aircraft weighing less than 12,500 pounds, the FAA does require us to do a complete inspection of everything, no less often than once every 12 calendar months. And if it were up to me to decide to design an inspection program for my aircraft, there would be lots of parts of the aircraft that I would say we really don't need to inspect every year. It would be okay to inspect every 2 or 3 years. And there are other parts of the aircraft, notably firewall forward, where you can't inspect often enough. Particularly, for example, in my aircraft, it's a turbocharged aircraft, and it's a family of aircraft that has a very, very high incidence of catastrophic exhaust system failure that has caused many fatal accidents. And so, we inspect the heck out of the exhaust every 50 hours, and if we could inspect it every 25 hours, we probably would. The FAA for bigger aircraft, for multi-engine turbines and for aircraft over 12,500 pounds, provides for a more complicated and flexible phased inspection program. But for smaller airplanes, they require that we inspect everything in the airplane once a year. And is that optimal? No. We just have to live with it. I'm not sure if that's what the question was getting at or not.
Sounds like a good answer. Roger has a question here. He says that I hear that you can't really hurt your engine running lean of peak or rich of peak at 65% power. What I'd like to know is, what is 65% power? How can you tell exactly what is 65%? Is that 60% of RPM redline?
Well, first of all, the 65% is sort of an approximation. It's really a question of internal cylinder pressure, and unfortunately, we don't have instrumentation on our engines to measure internal cylinder pressure. So what I tend to do, and in fact, I think the article in December Sport Aviation, my column in December, this December issue of Sport Aviation was about this. We use as a best approximation cylinder head temperature as our guide for how hard we're pushing the engine. And as a general rule, if your cylinder head temperatures, and this is true for most engines under most conditions, there are some extreme cases that would be exceptions, but for most engines in most normal outside air temperatures, if the cylinder head temperature is well below 400 degrees, say 380 or less, then we're not going to be hurting anything no matter what we do. So I teach, and my leaning webinar emphasizes this, that cylinder head temperature should be our principal our principal guide in terms of leaning procedure. A lot of owners lean with respect to EGT. I don't do that myself. I don't think it's a good idea, simply because in order to use EGT as a leaning reference, you have to establish what peak EGT is, and unless you're operating at very low power, peak EGT is a place you don't want to be at. So I recommend not using EGT as a leaning reference. I use cylinder head temperature as my primary leaning reference, and my personal target is not to let any cylinder head temperature on my airplane exceed 380 degrees. If I was flying a new generation airplane like a Cirrus or a Columbia or a Cirrus or Columbia or a Diamond that has a very, very efficient cooling system, I would probably lower that target from 380 to 360. But in fact, I set my engine monitor CHT alarm to go off anytime a CHT reaches 390, and if the alarm goes off, I do something to bring it right back down again. And I think my obsessive attention to cylinder head temperatures is one of the factors that has allowed me to get such terrific longevity out of my cylinders.
Awesome. Well, Mike, thank you so much for another excellent webinar. I kind of feel like we should all be receiving college credit, I think, for attending these webinars. These are such good and complete and thorough and detailed webinars. Thank you so much for your time tonight. To all the attendees, thank you so much for tuning in tonight. Looks like February 6th is your next scheduled webinar, and it's on how healthy is your engine. Just a couple comments about that, Mike.
Yes, well, it sort of segues into what we were talking about tonight. The RCM emphasizes condition monitoring, and we will be in the February session, we'll be talking about engine condition monitoring and the various tools that we use to keep tabs on the condition of an engine and trying to sort out what things are important and what things aren't important and so on. So it should be an interesting session.
Great. Well, I look forward to it. Mike, thanks again. Have a great night. To all the attendees, thank you so much for tuning in. Good night, everybody.
Good night, everybody. Thanks. Happy New Year.